Welcome back. In the last lecture, we started our discussion on the topic called packet classification. Just to refresh your memory, packet classification is done with a set of the rules, and the rules are written using the different attributes, be it the source IP address, destination IP address, and the transport layer protocol fields, and then the port numbers or any other additional fields that you want to add in. So we'll continue the discussion on the packet classification today as well. And the agenda for today's lecture goes something like this. We saw some of the data structures for implementing the rules of the classifier. And we saw one optimization that you can bring, particularly the something called as the set prune trie on the basic hierarchical trie structure, and we'll see one more optimization on that one today, and then we'll see some of the heuristic methods to do the classification, and we'll also look into something called as feed level trie, which is a different kind of the trie for doing the packet classification, and then at the end we'll look into the TCAM based how do we implement the packet classifier using the TCAM memory as well. So that is the whole agenda for today's lecture. A data structure called as the Grid-Trie. This is an optimization, as I said, on the hierarchical trie and even the set prune trie as well. So Grid-Trie is an optimization over the hierarchical trie and the Grid-Trie, set prune trie as well. So let's see what is the idea behind the Grid-Trie, and in order to understand that, let's take a simple example. Here is the classifier with the two rules with the two dimensions D1 and D2, and the rule R1 says the D1 is 0 0 star and then D2 is 1 0 star, and rule R2 says this is star and then N1 1 star. So these are the two rules in my classifier on the two dimensions. And first let's construct the set prune trie and then ask the question, what is the further optimization that we bring here. So as usual, I go one dimension at a time. So I'll start with the root node, and then on a 0 you come to the left, and on a 0 you come to the left. This 0 0 star is handled. I'll mark this as with the highlight. And then you go to the star, that is done by highlighting this node itself. So both the prefixes of the dimension D1 are now taken care. And now let's go to the second dimension. So D2's first rule R1 says you need to have the path for 1 0 star, and that can be done by having a no cost link to the another node, and then on a 1 you come to the right, and then on a 0 you go to the left. This is your rule R1. And rule R2 says this is star, so I just add a no cost link from the root node to this node directly, and then it says on 1 1. So this is a 1, first one, and this is the second one. So this is your rule R2. And now what we said is in the set prune trie, and if you happen to take, let's say you get the input as a packet which the source IP address, assuming D1 is the source IP address and D2 is the destination IP address, and this packet has got the source IP address starting with the prefix 0 0, and the destination IP address is let's say 1 0 star. Then on this 0 0 I traverse this path, it's well and good. On this 1 0 I traverse this path and then reach the node with the label R1. So that's fine. So we say that this is classified with the rule R1. But on the other hand, if you get an input to 0 0 star and then an 1 star, what was happening is on the first 0 0 you traverse the set of node, and then on this 1 1 we don't find a path here, so we're going all the back to the root node and then trying the alternative path. Instead of doing that, what we said is you add this node here itself and then label this with the rule R2, and so by you just avoid the backtracking. So that was the set pruning. So this set pruning trie was giving you optimization with the at the cost of the node replication. A simple question that we ask here is why to replicate the nodes? So instead of replicating the nodes, anyway a node with the label R2 exists here in the trie. Can I add a pointer to that node? Wherever I was doing the replication, just add that to a pointer to that node. Although it may not give a very big reduction in the storage space and the number structure of the trie, but nevertheless, anything that you can avoid is actually a good addition. So that's precisely what we do here in the Grid-Trie. So what we do is, instead of replicating the node, we actually add the pointer to the respective node itself, and thereby we actually try to avoid the node replication. And so this is how the Grid-Trie look like. On row 0, this structure is there, and this is highlighted, this is highlighted, and what I do is add the no cost link from here to this one, and no cost link from here to this one, and on 1 and 0, this is anyway representing R1, I retain that, and for this I require 1 and 1, I have this, label this with R2, and whatever the additional node that I was adding, that I am going to avoid by adding a link from here to this node itself, though this on the 1. So this is what the trie structure now look like, and this we call it as the Grid-Trie. So it is an optimization over the set prune trie in terms of the number of the nodes that exist inside the trie structure. So that is the thing. So we'll take a couple of more examples and see how much reduction specifically it can bring in terms of the number of the nodes, and although as I said it's not a very big reduction in the number of the nodes, but nevertheless there is some optimization. So here is a classifier with 5 rules, R1 to R5, and the values, the prefix values for the dimension D1 and D2 are shown here. And as usual, we go one level at a time, one dimension at a time, and construct the trie. So here is the node. So what represents this? Represents the by this star. The root node itself is highlighted, so that is okay. And this one 0 0. So this prefix is now taken care. And I continue. So 1 0 star is another prefix that you find, unique prefix that you find in the first dimension. These two are taken care. And there is a third unique prefix which is 1 1 star, which is here. So the first level trie structure is now done. So all the unique prefixes of the dimension D1 are now taken care. So as usual, we move to the second dimension and then keep adding the nodes as a descendant to these nodes. So what are the unique prefixes? 0 0 star is the another unique prefix, but that is applicable when the first level prefix is 0 0 star. I add a couple of nodes as a descendant to this node using a different kind of node structure. Here is the rectangle, and that I label it as R1. And another prefix on 1 0, the second level is 0 star, so that I'm going to have it here. And 1 0 star with the prefix 1 0 star is also there, so that I'm going to add 2 nodes here, 1 and 0. This I label it as R3. And similarly with that one, with 1 1 star and 1 1 star, I'm going to add 2 nodes here. And then with the for the star, I'm going to have 0 0 here. So this is the hierarchical trie structure for this these set of the rules in the classifier. So if I convert this into set prune trie, as usual, I'm going to replicate the nodes instead of the backtracking. So how does the set prune trie look like? So first level nodes are as usual, they are there. And the second level nodes are also as usual, whatever there in the hierarchical trie, all of them are here as well. So this is what the hierarchical trie was. And what I'm going to replicate now, the nodes which are actually to avoid the backtracking. So if let's say on the rule 1 0 star in the first case and then a 0 0 star in the second case would take you to the R1. This is 0 0, this is 0 0, 0 0, 1 0, 0 1, 1 0, this is 1 0 1, and then this is a 1. So the green color nodes are the ones which are replicated. So if we happen to read 1 0 in the first place and then a 0 1 instead of that one, so what we are saying is you need to, this is 0 0 star. So if your input packet contains the prefix 1 0 for the dimension D1 and 0 0 for the dimension D2, then the rule that is applicable according to this set of the rules is basically R5. That's why I replicated this node, and then I continue doing this. So on 1 1 star in the first dimension and 0 0 star in the second dimension will also take me to the rule R5, and these are the two rules that are replicable. So if you convert this into the grid trie, how the trie structure will look like. So as usual, the first level nodes are there for the dimension D1, and these are the 4 nodes which are highlighted corresponding to each of the unique prefixes in the dimension D1, and I add the nodes for the second level as well. So this is how the trie structure look like, and I was replicating on the left hand side node R5 was there, and instead of doing that, what I'm doing is I'm adding a link from this node R2 on the input 0 to this R5 itself, and there was another node here which was actually descendant of this node, which is going to the with the label 0 on the left hand side, that is also going to the node R5. So thereby adding these two links, basically I avoided replication of the 2 nodes in the trie structure. So that is what the grid trie is all about. So let's quickly take a look at another example. This is a classifier with the 7 rules, R1 to R7, and again there are 2 dimensions. As usual, the construction start with the first dimension and then I go further. So here I am directly constructing the set prune trie. So the first unique I 0 0 star. So this is the path for 0 0 star, and then you have a 1 0 star. So this is 1 and then a 0, and then you have on the second level a 0 star. 0 star is this node that is also taken care of, and then a star. So that will add the node in the second when you construct the for the second level node. So this is 1 1. So on the second level 1 1 is rule R2. 1 1 followed by 0 is R1. So that's why here it is. And on the 0 star, when you read a 0 followed by a 1, it is the R4. And on the 0 star, when you read 1 followed by 0, and this is the node R5. And if you happen to read only 1 star, then it is the rule R6, which is actually used for classification. And then if you happen to read 1 followed with 0 and then a 1 star will take you to the node R3. And this is the rule, the structures, the couple of things for the rule R7 on the 0 followed by 0 at the dimension D2. So all the unique prefixes of the level 2 or dimension 2 are also now taken care. So this is what the trie structure look like. Now we'll keep adding the nodes which are replicated nodes. So what are the replicated nodes? If you happen to read 0 0 in the first place and then a 0 0 for the second dimension as well, so that is classified with the rule R7. And if you happen to read 00 followed by 01 at the second level, then that is classified with the rule R4. R4 says 0 star. So 0 are here, R4 is here. So 00 star is actually a subset of the 0 star. That's why we are replicating it here. And then if you happen to read 00 followed by 10 star, so that is the rule R5, because again 0 star is a superset of the 00 star, so that's why we are replicating here. And then if you happen to read 0 star followed by a 00 star, that is R7. And if you happen to read 10 star in the first dimension and 100 star in the second dimension, that is R7. And that's the set of the rules. Basically 5 nodes are replicated in the set pruning trie. So now if you convert this into the grid trie, so how many nodes will be eliminated from the trie structure? Basically, as many nodes are replicated in the set pruning trie, those many nodes are eliminated. So basically 5 nodes will disappear from this trie structure, and those many number of the links I need to redirect to the respected nodes in the structure. So here is the one. So the first level and the second level trie structure. So it's done. Now I'm going to add the links which are missing or they replicated in the previous case. So from this node, remember only the last level nodes are actually pointing to the node, because I can read only one input symbol using the traversing that particular length. So if there are intermediate nodes, they need to be still replicated in the grid structure. That is what is done here. Similarly, on the input 1, so you are replicating the node R4. So I added a link to the R4, and from this one on the 0 on the left hand side, it was going to R5. So I added a link to the node R5 itself with the label 0. And from here on the input 0, I was going to the R7. I added that. From here on the input 0, I was going to the R7. So that's also replicated. So that is the whole structure. So basically there are 5 links which are added to the structure. So this is one optimization that you can bring use by little modification to the hierarchical trie and the set trie. So that's how this classifier is actually going to work using the grid trie. So if you have a very large number of the nodes being replicated in the trie structure, then this trie structure, grid trie, will actually help in the reduction of the number of the nodes. Okay. So with that optimization, let's move on to the next type of the optimization that you can bring onto the table. This optimization is something called the extended two-dimensional trie. What is shown here is a set of the rules organized according to the something called the source and destination address. So there is a laundry list of the IP address. Let's say I got the rules from R1 to R100 or the number all. What the idea here is, when you take the set of the rules, and most commonly the source and destination IP address are the two components of the any rules that you write, and even if you have thousands of rules, and when you pick up one particular packet and inspect the source and destination IP address fields, I don't have to, not many number of the rules are actually matching for among the combination that I have. I have 1000 rules in all, but if I pick up one particular source and destination IP combination, there are only handful number of the rules which actually are candidates for matching. So the idea here is I segregate or divide all the rules in my classifier first based on the source and destination IP address combination. What I mean by that is, so these are the set of rules from R6, R12, R15, R20 and R54 are the rules which are applicable for this unique source and destination IP address combination. And these are the set of the rules which are applicable for source and destination IP address S2 and D2 combination, and so forth. So if I have n number of the rules in my classifier, I find out first in the first place what are the unique combination of the source and destination IP address fields or unique prefixes of the source and destination IP address field, and then segregate the rules which are applicable for that combination only. You might have some reduction in the case, but nevertheless, you can actually, when I am saying the S1, D1, it is actually the complete IP address. The prefix part you can expand and then bring the unique combination of the source and destination IP address, then organize the rules which are applicable for that particular combination into the structure. So then we know that there are some data structures which allow you to do the two-dimensional comparison. For example, hierarchical trie or the Grid-Trie or the other structure I can use. So instead of assuming if I have multiple dimensions, source and destination IP address are the two components, but there are a bunch of other fields, dimensions also in my classifier, and I build a data structure for two-dimensional classification or in the first place. So that is the first level identification that you do. And then in the second case, what I do is once I narrow down which of these among the list which you need to compare, I actually linearly I can go and search one by one, because assuming these are not many number, I can afford to do that. So that is the whole idea behind the two-dimensional extended two-dimensional trie structure. So basically, you do a first search on the source and destination IP address field, which are commonly found in most of the rules, and then you go ahead and check linearly one by one the other fields which are applicable in the sets. So that is the otherwise this is exactly same as that of the hierarchical trie and the other Grid-Trie and the so you can use any of those data structure to build such. This is an heuristic approach. This originated from after studying the many classifiers found in the commercial routers of the network service providers. The people found out that this is actually indeed a better method to organize these so that I can minimize the overall number of the such operations. So that's the heuristic approach. This also you can bring in to increase the speed of the classification that the routers do. So with that, let's move on to the next data structure. This is something different, something called as the field level trie structure. So the field level trie structure, basically it is also kind of the heuristic, but what it does is it starts with all the rule sets in the classifier. At the beginning, you assume that every rule is equally a potential candidate. And I take the one dimension at a time and then try to segregate what are the rules applicable. If that prefix is matched, these many reductions, these are the only candidates which are which need to be further examined. So that is what the field level trie structure do. So first let's understand what is the data structure, and then we'll take an example and see what is the how the trie structure look like. So every node in the trie structure has set up applicable rules. Earlier in the previous case, the node was labeled with the every path, every link between the nodes were actually having one bit of labeling. Instead of that, what we do here is the multiple number of the bits, in fact the whole prefix itself, and then if this prefix is matched, these are the number of the only rules you need to examine. So I start with the root node, which is having the entire set of the rules in the classifier, and then let's say 00 star is one prefix at the dimension D1. With the 00 star, what are the now applicable rules? A subset of the rules in the root node would be the second level node. So like this, I continue doing that. One dimension, second dimension, third dimension, whatever the number of dimensions I have, I keep dividing the rule set into multiple pieces, and then finally when I hit the leaf node, I get one particular rule which is applicable for that particular packet. So every node in the structure indicate the applicable rules, remember in the hierarchical and the set prune trie and the grid trie, at every leaf node only one node, when you highlight it, there is only one rule that is applicable, but here it can be the intermediate nodes can indicate more than one number of the so a node at the level I generates the child nodes considering the values in that particular field. What is the prefix that is you are considering right now? Using that, it is going to add what are the child nodes corresponding to itself. If the field value, meaning if the dimension D1 or D2, whatever I am saying, sometimes you will have the source and destination IP address I can express in the form of the prefix, but sometimes if you use the other fields like the port numbers, they not necessarily be in the prefix format. If there is a prefix format, then for that prefix you will have the child node. And if the field value is expressed in the range, particularly if I say that the port number need to be in between 5 and 10, then for that range I am going to create the, for every unique range I am going to create the child node. And at any level, if there are, let's say I take the path 1 and then say that actually this is the R1, R2 are the rules that are applicable, and then when I go to the second level, only on some prefix only R2 is applicable. And when I traverse the other particular path, maybe from that also I might get on a certain prefix only node rule R2 is applicable. So instead of creating the two nodes at the level, if there is a rule which is having the unique combination, not necessarily only R2, even if you think that R1 and R2 are the unique combination at the 8th level, only one node with the label R1 and R2 is included at that particular level. So that's how this field level trie works. So let's see with a simple example how the trie actually look like. Let's again assume there are two dimensions D1 and D2, and rule R1 is having the prefix 0, 0 star and 1, 1 star, and rule R2 is having 0, 1 star and 1, 0 star, and rule R3 is saying 1 star and 0, 0 star, and rule R4 is saying this is star and 0, 1 star. So what do we need to do? As I said, you need to start with the root node. Root node is assumed to have, now when you begin, every rule in the classifier is equally likely to be the candidates for the match. So now what are the unique prefixes in the first? I go one dimension at a time. So I take this dimension and I look at the unique prefixes. So for example, here the first unique prefix is 0, 0 star. I add a link here with 0, 0 star. What are the potential rules that are applicable? So one is obviously R1 is applicable. It depends on the second dimension. But as of now, R1 is applicable. And also star also is a superset of 0, 0 star. So that might also be the candidate. So I write R1 and R4 as the potential candidates for this prefix 0, 0 star. Now from the 4 rule node to the 2 rule node we have added. And I keep going further. So on the prefix 0, 1 star, what are the potential candidate rules applicable? R2 is one candidate, obviously, and so is R4. So because star is a superset of 0, 1 star, so that is still applicable. And I continue doing this. So on the 1 star, you have got R3, and 1 star is not a superset of the R1 and R2, no question of that. So still 1 star is a subset of the star, so I include R4 as well. If none of these prefixes match, then you take the star route and then go to the node. Only here R4 is applicable. So that is the division. So using the unique prefixes at the first level or first dimension, you branch out and then create the unique set of the rules in the second level. Now what I am going to do is I am going to examine the second dimension, and using that as an input to the nodes at the first level, at this level, I am going to again create further division. So if this 1 star is one applicable prefix for the rule R1, so on the 1 star rule R1 is applicable. So remember, this R4 is not applicable now because that prefix, that requirement is 0 star. So and if 0 star is found, then the rule R4 is applicable. So I write that as a separate node. Similarly, on this node combination R2 with R2, R4. So if you happen to read 0 star in the second level, then R2 is applicable. And on the other hand, if you happen to read 0 star, then this is applicable. So this is what I was telling. At a particular level, now R4 is branching out from the R1, R2 node as well, and R2, R4 node as well. We don't repeat R4 many number of times, only one time, but just the pointer we're adding. So for R3 as well, on the 0 star, only R3 is applicable, and on the 0 star again, I am going to this particular node itself. And again on 0 star, so in the second dimension, I am going to this node. So this is the trie structure for the field level trie structure for this particular classifier with the 4 roles. So basically the segregation is shown. So this is the case when the none of the dimensions or values are expressed in the form of a range. When you don't, particularly to be more precise, when you don't have the port value expressed in the form of the ranges, but they are not very unlikely to appear in any of the classifiers. So let's take an example or add a little bit one more dimension to the same example, and then see how do we actually add the ranges as well. So this was our case. So earlier I had 2 dimensions. Now I am going to add the third dimension. Rule 1 says 0 star, and then this is 1 star, and the port number range is 4 to 8. And rule R2 says this is 0 star and 10 star on the second dimension, and the port range is 1 to 2. And rule R3 says this is 1 star and the second dimension is 0 star, and the port value is exactly 10. And R4 is a rule which is first dimension is a star and the second dimension is 0 star, and the port number is exactly 5. How do we construct the field level trie for this kind of the rule, which is having the some of the rules are having the port ranges. So the idea is again very simple. Let's go and try to construct the so all 4 rules are equally likely candidates at the root node. So you have them, and now again look at the unique combination for the dimension D1. So 0 star, you got R1 and R4, and on the 0 star in the first dimension, R2 and R4 are the candidates, and on the combination 1 star, R3 and R4 are the candidates, and on the star only R4 is the candidate. That is the division. Now I keep doing the same thing that I was doing earlier. So again R1 on the 1 star, only R1 is applicable, and but on the same 0 star prefix, but if the input happens to be 0 star in the second dimension, then the R4 is applicable. And from this node on the 0 star, again this applicable, and on this node with 0 star, this is going to R4, and anyway this is going to on 0 star, this is going to R4. And from here on the input to 10 star, I am going to the node R2, and from here on the input to 0 star, I am going to the node R3. So this is the set of nodes that I have for the So now for the rule R1, what is the port range that is applicable? 4 to 8. All that I write is, I write this range in between 4 to 8 rule. R1 is applicable, and for this case, this is exactly need to be 5. Then the rule R4 is applicable, and this is R2. For R2, this need to be between 1 to 2. On this range, the rule R2 is applicable. For R3, this need to be exactly 10, and then this is the node. So this is a very simple case where the ranges are not overlapping, but it is not always the case. So for example, if two similar prefixes 00 star, 11 star as the R1, 00 star and 11 star as the R2. But for the first rule, the port number is 1 to 10. For the second rule, port number is 5 to 20. Then there is a portion which is actually overlapping. So some portion is going into the R1, some portion is coming to R2, and some portion is actually overlapping. You need to handle those cases as well.